There are still some questions that we need to answer about this algorithm. The first one is, how do we handle sorting the independent subarrays? So when we say we want to 5 sort the array and we pick the elements that are 5 apart from each other and sort it, how do we actually sort those sets of elements? Well, it actually turns out that we can use insertion sort for it. What we find is that when the size of the array is very small, insertion sort is actually very, very efficient. So we can use insertion sort for these smaller sets, and it does not have a negative impact on our running time. Another question that we need to ask is, how do we determine the increment sequence? We mentioned before that any increment sequence works, but some sequences are better than others. So how do we pick it? Well, a very popular choice is one that Shell actually recommended. His idea was that we let h of t be the floor of n over 2, and we let h of k be the floor of hk plus 1 over 2. So what does that mean? What we're basically saying here is h of t minus 1 is going to be the floor of ht over 2, or we just keep dividing by 2. So we pick h of t to be n over 2, and each increment in the sequence, we just keep dividing by 2 over and over again, and if we need to, we take the floor of it. Here is our code for shell sort that uses that increment sequence. So if we take a look at the first for loop, we find that we have this variable called gap, and that's going to tell us how far apart are we going to be sorting these elements. So we see that's initially n over 2, and then whenever we go to the next iteration, we take that gap and divide it by 2. Remember, divide equals means, in this case, gap equals gap divided by 2. But the body of this loop, what we're doing here is actually insertion sort. If you look at this code right here, you'll find that's insertion sort. That's all it is. It's just now that we're sorting the specific elements in our gap. Unfortunately, what we're going to find is that Shell's increment sequence is actually a pretty poor approach. We'll see that there are other increment sequences that give us a much better improvement in the algorithm's running time. So unfortunately, just having it be n over 2 doesn't work very well. Now, the thing about shell sort and what we saw is it's really easy to code. That's the good news. The bad news is coming up with the analysis is very tricky. And that's because the running time of the algorithm actually depends on how we set up the increment sequence. In fact, the average case analysis is an open problem. No one has actually come up with the answer to the average case analysis for shell sort, except for some very trivial increment sequences. So what we're going to do is we're going to look at the worst case bounds for two particular increment sequences. And we're not going to worry about the details on the proofs of those bounds because, quite frankly, they're very advanced. We're just going to look at, here's the bounds and here's what the running times are for them. Let's start by taking a look at Shell's increment sequence. And what we find is the worst case running time is theta of n squared. So think about that for a second. With Shell's increment, shell sort is no better than bubble sort, insertion sort, or selection sort. And the reason why this is the case is because with Shell's increments, the pairs of the increments are not relatively prime. Now, what do we mean by that? We say that two numbers are relatively prime if the only number that divides both of those numbers is 1. So we're not saying the two numbers themselves have to be prime. They can be, but we're saying that the two numbers are only divisible with each other by 1. And what this means is that when we get to the smaller increments, they're not very effective in our algorithm. Another increment sequence was suggested by Hibbert, and this actually does give better results in practice. So his increments were 1, 3, 7, all the way up to 2 power k minus 1. So we would start with 2 power k minus 1, then we would go down and further until we get down to 1. And the key difference with this particular sequence is that the consecutive increments have no common factors. So this does help with reducing the number of comparisons. With this increment, the worst case running time is theta of n3 over 2, which is, it's pretty decent. I mean, it's not n squared, so that's a good thing, but it's It's better. I wouldn't say it's the best, but it's a pretty decent one in practice. In fact, it's believed that the average case running time is O of n 5 over 4, but no one has been able to actually prove this. These two sequences are not the only increment sequences. There are others, and there are a couple particularly that are slightly better than Hibbert's increments in practice. The problem with these particular increment sequences, though, is that they're a lot more complex to compute. They're more complicated to come up with the formula. So what we find is the performance of shell sort overall is pretty decent. It's actually quite acceptable in practice, even when n is in the tens of thousands. And the reason why there is this popularity with it is because the code is very simple. Since the algorithm is very simple to implement and we get a decent performance, the algorithm is recommended whenever we're trying to sort up to a moderately large input. Now, when we get to substantially large inputs, shell sort's probably not the best, but when we're dealing with moderately sized inputs, it's one of the more recommended algorithms.